Dear students, the next topic is design of synchronous counter. Okay, so we all know that, as discussed, what is a counter, right? And what is a synchronous counter. So let me quickly brush what we have discussed earlier. So we know that a counter, as I told, is a register, correct? It's a register which is capable of counting. That is the main task of a counter. It is capable of counting the number of clock pulses. The number of clock pulses, okay? So this pulses where it counts when it arrives at its input, at its clock input. So this is what is the counters, okay? Now we are going to design a synchronous counter. Now we know that it is a register which is capable of counting the number of clock pulses when it arrives at the clock input, correct? So we have two types of counters. So one is called the synchronous counter, okay, and another one is called as asynchronous counter, okay. So we have problems to be designed in both the sessions, okay. We have to design it using the synchronous counter and also the asynchronous counter, okay. So synchronous counter is a type of a counter. There is no connection between output of the first flip-flop and the clock input of the next flip-flop, okay. That is, all the flip-flops are clocked simultaneously in case of your synchronous circuit. That is, in case of the synchronous counters, okay. So all the flip-flops are clocked simultaneously so that you understand it better, okay. So it is clocked simultaneously, okay. Here it is not clocked, okay. All the flip-flops are not clocked simultaneously. So this is one of the major, operation of synchronous counter and asynchronous counter, okay. That is, when the counter is clocked such that each flip-flop in the counter is triggered at the same time. That is what is your synchronous counter. That triggering occurs at the same time is called as your synchronous counter, okay. But whereas, in case of your asynchronous, that doesn't happen, okay. So that is what is the speciality of your asynchronous counter. Clear? Now, when we have to design a synchronous counter, there are certain procedures that we'll have to follow, okay. Now let us take an example problem, okay. So let us design a mod 5 synchronous counter, okay, synchronous counter using JK flip-flop, using JK flip-flop, okay. And let us also draw its timing diagram. So this is what is the question given to us, and they have specifically mentioned use only the JK flip-flop. Now in the previous session, when we saw the design of synchronous sequential circuit, they asked us to design it using T flip-flop. Here they're asking us to use JK flip-flop. If nothing is being mentioned, we can go ahead and use any flip-flop of our choice, okay. Now we'll have to determine the count a mod 5 counter can count, okay. So when I say mod 5 counter, okay, so the counting process starts from 0, 1, 2, 3, 4, and see here, this completes our 5 state, correct? 0, 1, 2, 3, 4. So it is 1, 2, 3, 4, 5. So 5 states is over. So it will count from like 0, 1, 2, 3, 4. So from 5, 6, 7 state, you have something called as the tone case, okay. That is, I'll explain it to you all in detail. So the first thing which we have to take it is decide the number of flip-flop required to design the counter. Okay, so how to decide the number of flip-flops required? So you can use the expression to raise the power of n greater than or equal to n, where n is the counter number, right? So this is nothing but 5, mod 5 counter. So 2n raised is equal to 5. So what will be the value of n that decides the number of flip-flop? So it is 5, because you have it is greater than, greater to, equal. So the number of flip-flops used is 3. And since they've already told us JK flip-flop can be used, so this 3 will be split as JA, JB and JC. Correct? Now the next step is we'll have to decide the excitation table of a counter. Excitation table of counter. Okay, which is very important. So how do I do this? How do I obtain the excitation table is, you will have to have present state, the next state which I'll write as NS, and the flip-flop inputs. Okay, so the present state, let me name it as QC, QB and QA. I am writing it as in this order. Okay, and the next state, let me write it as QC plus 1, QB plus 1, QA plus 1. Okay, and our flip-flop inputs will be JCKC, JBKB and JAKA. Okay, now this is the outline of my JK flip-flop. I'm sorry, the excitation table of the counter. Okay, now we have the counts, like you have from 0, 1, 2, 3, 4, 5, 6 and 7. Okay, and the counter counts, as we know, for 0 it counts by 1, so here it is 1. For 1 it is 2, for 2 it is 3, for 3 it is 4, for 4 it is, it is 0. Correct? Because the mod 5 counters count from 0 to 4, right? So it is 0, 1, for 1, 2, for 2, 3, for 3 it's 4, and for 4 it is 0. Okay, and from 5 you have the don't case. Okay, so the counting process is 0, 1, 2, 3, 4. 0, 1, 2, 3, 4. So when the 5 states is achieved, it will start counting don't case. Okay, now how do I fill this JCKC, JBKB and JAKA? Okay, so this table can be filled with the help of excitation table of JK flip-flop. So let me recollect the JK flip-flop excitation table which we have already discussed in the basics of flip-flop. Okay, so let me recollect it for you all soon. You have Qn plus 1, J and K. So here it is 0, 0, 0, 1, 1, 0, 1, 1. So what are the inputs? 0x, 1x, x1 and x0. So this is what is your excitation table of JK flip-flop. Okay, so to fill this JCKC, my inputs will be QC and QC plus 1. Okay, so QC and QC plus 1 will give me JCKC. Clear? And QB, Q plus 1 will give me the inputs JB, KB. Similarly, QA plus 1 will give me JAKA. Okay. So you can have your fingers across these two columns to fill up the table. Okay. So 0, 0 out of your excitation table of JK will give you 0x. Okay. Next, again 0, 0, 0x. See, you can bifurcate your rows like this, otherwise you will have confusions because everything is dealing with zeros and ones. Okay, so let me bifurcate this page for you all. 1 minute. So let us quickly fill up this excitation table of the counters, which is very important, using the excitation table of JK flip-flop. Okay, so here comes 0, 0 again, 0x, 0, 1, it is 1x. Okay, so 1, 0, it is x1. Okay, so 1x, so 1 minute, it's all don't case because we don't have the conditions specified for the don't case. Okay, now coming back to JBKB, you'll have to consider the inputs QB and QB plus 1. So 0, 0 gives you 0x. Okay, then you have 0, 1 which gives you 1x. Similarly 1, 1 which gives you x0. Okay, so let me fill up this column for you all fast. So then you have x1. Okay, and then it is 0x, and then it is full of don't case. Now let me come to JAKA. So considering QA, Q plus 1, 0, 1 is 1x. Okay, so you have 0, 1, 0, you have x1. For the next case you have 1x and x1 and 0x, and remaining inputs you have don't case. Okay, so let me write that for you all. QC plus 1 gives you KC, JC, KC. QB plus 1 gives you JB, KB. QA plus 1, that is the present state and the next state of your A input, gives you JAKA. Okay, so this is how you complete, using these inputs you complete your excitation table of counter. Okay, then the next is representation of K-map. Let me turn the page for you all. Then the representation of K-map using the inputs of JA, JC, KC. Let us design for JC, KC first. Take the inputs of QC, QB and QA. Okay, since we have 3 inputs, so you know it is something like this. Okay, so let me represent the K cells for you all, and similarly for KC you have the cells like this. And since you're familiar with K-map, I shall quickly do that for you all because we have solved n number of problems in this. Okay, so taking the inputs of QC, QB and QA, you have something like this, and rest all with don't case. And for KC you have don't case and only one over here. So let me group this. So I can group this way, and here I can group this way, the entire group. So for JC you have QB, QA, and for KC you have 1 because you have all the 8 as one single group. Okay, for JB, now coming for JB, let me quickly do for JB. Now let us let us get the expression for JB. Okay, so let me do that quickly. QC, QB, QA. Let me write the inputs. Okay, so it is 0, 1, x, x, 0, x, 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 the don't case. So this will be my group. And for JB I have the expression as QA, and for KB, let me draw it. You have QC, QB, QA, 0, 1. Students, this I am doing it quickly because we are very much familiar with the K-map concept. Okay, and grouping also we are quite familiar, so that is why I am just doing this quite quickly. And for JA, sorry, it is for JB, and KB is over. Now it is for JA. So here it is QC, QB, QA, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. So the inputs are 0, x, x, x. So here for JA you have something QC bar. Okay, and for KA, the final expression, for KA we have QC, QB, QA, 0, 0, 0, 1, 1, 1, 1, 0. Here the inputs are, okay, these are the inputs. So you have one term and K will be 1. Okay, the final step is to draw the logic diagram, which is very simple. Okay, so the main crucial part is to complete the excitation table for the counter. So once we are done that, and simplification of K-map and the logic diagram is quite simple. Okay, so here we have JA, JB and JC. Okay, so your JA, KA, QA, QA bar, JB, KB, QB, QB bar, okay, JC, KC, QC and QC bar. Okay, so let me have a common clock pulse for all this. Okay, so and let me fill the expression. So JA, the expression for JA is 1, correct? So JA, the expression for JA is QC bar. So I'll just connect this over QC bar, okay? And the expression for KA is 1. So I shall write this as high because it signifies 1. Similarly, KC is 1. So I'll write this as high, okay? Next I have JC as QB and JC as QB, and where is my JC? JC is QB and QA. Okay, so let me get this here over here and join this using a AND gate so that it comes to JC. Okay, now JB is QA. Okay, so JB is QA. I can connect it over here. So JB is QA and JC is QB, that is over. KC is over. JB is over. JA is over. So the representation of logic diagram is over. Okay. So JA, JB, KB. I think I've left out KB. So KB is nothing but a QA. Okay. So I can bring something like this or connect this to QA. Okay. So I think my logic diagram is complete in all aspects. Okay. So, and they have asked us to draw the timing diagram. Okay. So the timing diagram is very simple. I shall draw it for you all. So the timing diagram is, let us consider the clock pulse. Okay. So considering the clock pulses. Okay. So my clock pulse is valid. So this is my 1, 2, let me name it as 1, 2, 3, 4, 5, 6. Okay. Now for QA, QB, QC. Okay. Now you will have to have the reference as your excitation table of the counter. For QA, Okay, for QA, the sequence of counting for the QA, it is 0, 1, 0, 1 and 0. Okay, so how it counts based on the count sequence, I'll have to draw it. Okay, so the first count is 0. Okay, and then it is 1 for the count 2. Okay, then it goes to 0, then it goes to 0. Okay, and then again for the fourth count it goes to 1. Okay, and then 0 for count 5, then again it is 0. Okay, so this continues. So here it is 0, 1, 0, 1, 0, 0. So this QA is just the representation of the input, that is the condition of the present state, okay, for the count sequence from 0 to 4, that is 0, 1, 2, 3, 4. So what is the count sequence for that particular condition is this, and this is got from your excitation table of a counter. For QB, the count sequence is 0, 0, 1, 1, 0, 0. The same thing I'll represent over here. 0, 0. Okay. Next is 1, 1. And then it is 0, 0. Okay. 0, 0, 1, 1 and 0, 0 for QB. For QC it is, you can just check the excitation table that we have derived. For QC it is 0, 0, 0, 0 and then 1. Okay. So here it is for QC it is 0, 0, 0, 0 and then it is a 1 and then 0. Okay. So this is my status of count of QC. Okay. Here you can write the counting sequence. Okay. So 0, here the count sequence is 0, here it is 1, here it is 2, here it is 3, here it is 4, okay, and then again it's 0. So this is what is the timing diagram of your mod 5 synchronous counter. So this completes your entire problem. So students, you have to take care for any design of any synchronous counter. Now we have designed for mod 5. Any counters they ask you of any mod, okay, size, this is the same procedure that holds good for every circuit. Okay. In case if they are asking you mod 7, so the counting sequence will be from 0, 1, 2, 3, 4, 5, 6. Okay. And the rest all is supported by your tone case. So exactly the same procedure. Hope you understood this particular topic. Thank you.